Imagine holding a perfect circle in your mind, not a drawing of a circle, not a round object, but the pure mathematical concept, all points equidistant from a center. This circle has infinite precision. Its circumference is exactly pi times its diameter, where pi is an infinite, non-repeating decimal. No physical circle can match this perfection. Even atoms aren't perfectly circular. So where does this perfect circle exist? In your mind? In some realm of abstract forms? Or does it not truly exist at all, just a useful fiction we created? This question leads us to one of the deepest mysteries in all of human thought. Is mathematics something we discovered, like a mountain that existed before we found it? Or is it something we invented, like a hammer we created to solve problems? The answer shapes how we understand reality itself, consciousness, truth, and our place in the cosmos. And after 20 episodes exploring the history of mathematics, from ancient counting systems to quantum mechanics, from zero to imaginary numbers, from Fibonacci to fractals, we finally arrived at the ultimate question. What is mathematics? This is our season finale, and we're going deep. This isn't just about math, it's about the nature of existence, the limits of human knowledge, and whether the universe has a hidden structure that our minds can access, or whether we're creating meaning in a meaningless cosmos. Let's begin with the case for discovery. When you prove that the square root of 2 is irrational, you're not making a decision or stating an opinion. You're uncovering a truth that was true before you proved it, true before humans existed, and will remain true even if humanity vanishes. The proof demonstrates that you cannot express the square root of 2 as a ratio of whole numbers. This isn't something we decided. It's something we found. Mathematicians report that doing mathematics feels like exploration and discovery. They describe finding unexpected truths, being surprised by results, and feeling constrained by mathematical necessity. You can't just decide that 2 plus 2 equals 5. The mathematics itself pushes back, refuses to cooperate, insists on its own internal logic. Roger Penrose, the mathematical physicist, is he believes in a world of mathematical forms that exists independently of physical reality in human minds. In this Platonic realm, mathematical truths are eternal and unchanging. The Pythagorean theorem was true before Pythagoras, true before Earth formed, true before the universe began. When mathematicians discover a new theorem, they're not creating it. They're accessing this timeless realm of mathematical truth. Just as Columbus discovered America, which existed before he arrived, mathematicians discover theorems that existed before anyone proved them. This view explains some puzzling facts. Why do mathematicians from different cultures, working independently, discover the same mathematics? Chinese, Indian, Islamic, and European mathematicians all developed similar mathematical ideas. They discovered the Pythagorean theorem independently. They all found the same value of pi. They converged on the same mathematical truths. If mathematics were invented, you'd expect different cultures to invent different mathematics, like they invented different languages and different technologies. But mathematical truth seems universal. A circle's circumference divided by its diameter equals pi everywhere in the universe, for any being capable of understanding the question. Discovery also explains why mathematics works so well to describe physical reality. If mathematical structures are real and the universe follows mathematical laws, then of course mathematics describes the universe accurately. We're not imposing mathematics on nature. We're discovering the mathematical structure that is nature. The argument from discovery is powerful, but the case for invention is equally compelling. Consider this. Mathematics is done by human minds using human concepts expressed in human languages and symbols. The axioms we choose, the questions we ask, the proofs we value, all reflect human choices, human interests, human aesthetics. There's nothing in nature that tells us to study prime numbers or topology or group theory. We invented these fields because they interested us. We created the definitions, chose the axioms, and decided which theorems were worth proving. Different mathematical systems are possible. Euclidean geometry assumes parallel lines never meet. Non-Euclidean geometries reject this axiom and explore. What happens when parallel lines can meet or diverge? Which is true? Both are valid mathematical systems. We invented both and choose which to use depending on our purposes. Even basic arithmetic involves choices. We use based in counting because we have 10 fingers. Cultures have used other bases. Computers use binary. The Mayans used base 20. None is more true than others. They're different invented systems. The formalist view, championed by mathematicians like David Hilbert, says mathematics is a game played with symbols according to rules. The symbols don't mean anything. They're just marks on paper or screen. The rules are arbitrary, chosen by humans. Mathematical truth just means following the rules consistently. On this view, asking whether mathematics is true is like asking whether chess is true. Chess isn't true or false. It's a game with rules. Mathematics is similar, a sophisticated game we invented, with more complex rules and more interesting patterns, but ultimately a human creation. Social constructivists go further, arguing that mathematics is shaped by culture, history, and social forces. What counts as a valid proof has changed over time. Greek geometers required different standards than modern algebraists. The mathematics we develop reflects our technological needs, our philosophical assumptions, and our cultural values. The invention view explains why mathematics has limits and controversies. If mathematical truth were simply there to be discovered, wouldn't all mathematical questions have definite answers? But they don't. Gödel's incompleteness theorems proved that any consistent mathematical system has true statements that cannot be proven within that system. There are mathematical truths we can never know, and mathematicians disagree. Is the continuum hypothesis true? Does infinity come in different sizes? Should we accept the axiom of choice? These aren't settled questions. Different mathematicians make different choices, creating different mathematical universes. So we have two strong cases. Discovery explains universality, necessity, and applicability. Invention explains creativity, cultural variation, and human agency in mathematics. Perhaps the answer is both, or neither. Let's explore some middle positions. Mathematical. Intuitionists following Brouwer argue that mathematics is a mental construction but not arbitrary. Mathematical truth is what the human mind can construct through valid reasoning processes. Mathematics is neither discovered in an external realm nor freely invented. It's constructed by minds following necessary patterns of thought. On this view, mathematics exists in minds, but not just any mind can construct any mathematics. Human cognitive architecture constrains what we can construct. The fact that humans across cultures construct similar mathematics reflects our shared cognitive structure, not an external mathematical reality. Aristotelian realists take another middle path. They reject Plato's realm of forms but argue that mathematical properties are real features of physical objects. Circles exist in the world, planetary orbits, ripples on water, tree rings. When we abstract the concept circle, we're discovering a real pattern that exists in nature. Mathematics is discovered, but not from some otherworldly realm. It's discovered in the patterns, structures, and relationships present in physical reality. 3 sheep exist. Threeness is a real property of that collection. We abstract the concept 3 from many experiences of 3 things. Structural realists argue that mathematics describes structures and relationships. What's real are the patterns, not the objects. An atom isn't a tiny solar system, but atoms have structure, and mathematics describes that structure. We discovered the structures in nature, then invented mathematical languages to describe them efficiently. On this view, discovered and invented aren't opposites but partners. The structures are discovered. The descriptions are invented. Mathematics is like a map. The terrain is discovered. The map is invented. A good map corresponds to terrain, but many different maps can represent the same territory. Let's consider what's at stake in this debate. Why does it matter whether mathematics is discovered or invented? First, it affects how we view mathematical knowledge. If discovered, mathematical truths are objective, eternal, and independent of us. We can be wrong about mathematics, but mathematics itself cannot be wrong. This gives mathematics a privileged epistemic status. If invented mathematical knowledge is more like engineering knowledge. It's useful, reliable, within its domain, but ultimately conventional. We created it to solve problems, and different problems might call for different mathematics. Second, it shapes how we understand the relationship between mathematics and reality. If mathematics is discovered and describes reality accurately, this suggests reality has an inherent mathematical structure. The universe is rational, comprehensible, orderly. If mathematics is invented, its success in describing nature is more puzzling. We invented a tool, and surprisingly, it works. This might be because we designed it to work, or because we only notice the parts that work, or because the universe happens to have regularities that our invented mathematics can approximate. Third, it influences how we approach mathematical education and research. Should we teach mathematics as discovering timeless truths, or as learning useful tools humans created? Should mathematicians search for truths or create useful systems? Fourth, it touches on consciousness and human nature. If humans can access a realm of mathematical forms through pure thought, this suggests something remarkable about consciousness. Our minds can grasp eternal truths independent of sensory experience. We're not just physical beings but have access to abstract reality. If mathematics is invented, consciousness is creative but confined to the material world. We're clever tool makers but not mystical truth accessors. Let me share a perspective that integrates these views. Perhaps mathematics is the interface between mind and reality. It's neither purely discovered nor purely invented, but emerges from the interaction between thinking beings and a structured universe. Here's the idea. The universe has structure. It's not random chaos. Objects have properties, relationships follow patterns, causes produce effects. This structure exists independently of minds. Conscious beings capable of abstract thought can recognize patterns in this structure. We notice that 3 apples and 3 chairs share something, threeness. We abstract the concept of number. We discover that numbers relate to each other in patterns. You can add them, multiply them, factor them. But the particular way we formalize these patterns, our axioms, our theorems, these are invented. We could have developed mathematics differently. Aliens might have equivalent but different-looking mathematics. So the patterns are discovered. The formalizations are invented. Mathematics is the bridge our invented formalisms build to discovered patterns in reality. This explains why mathematics feels like both discovery and invention. When you're working out a proof, you're inventing a particular argument using particular notation, but you're constrained by patterns you didn't create. The proof works or doesn't work independent of your wishes. You're discovering which invented paths lead to valid conclusions. It explains why mathematics is universal. The underlying patterns are real and universal. Different beings might formalize them differently, but they're describing the same patterns, so their mathematics will ultimately be TRANSLATABLE. It explains applicability. Mathematics works because it describes real patterns, but it's not mysterious. That our invented mathematics works because we invented it specifically to describe patterns we observed, and it preserves both human creativity and objective constraint. We're creative in how we formalize, which questions we ask, which methods we develop, but we're constrained by the patterns in reality that push back against our inventions. Consider a specific example. Prime numbers. Are they discovered or invented? The pattern of primeness numbers, divisible only by 1, and themselves, exists in the structure of multiplication. If you have multiplication, you have primes. This pattern is discovered. But calling them prime numbers, developing prime number theory, proving theorems about primes, creating notation for discussing them all, this is invented. An alien civilization would discover the same pattern. They might not call them primes. They might not use base 10 to write them. But they'd recognize the same mathematical structure. Or consider imaginary numbers. We invented the symbol I and the name imaginary. We chose to extend the number system to include square roots of negative numbers. That was invention, motivated by solving equations. But once we made that choice, we discovered that imaginary numbers have profound structures. Complex analysis reveals stunning patterns. We can't make imaginary numbers behave however we want. They have properties we discover, and shockingly, these invented numbers describe real physical phenomena. Quantum mechanics requires complex numbers. Electrical engineering uses them. We invented imaginary numbers, but we discovered they describe reality. This suggests mathematics is neither purely discovered nor purely invented, but participates in both. We invent the tools. We discover what the tools can build. There's a beautiful paradox at the heart of mathematics. It's the most certain knowledge humans possess. Mathematical proofs are more reliable than any scientific theory. Yet we can't even agree on what mathematics is: discovered, invented, or something else. This paradox might tell us something profound. Maybe the question discovered or invented is too simple. Maybe it assumes a false dichotomy between mind and world, subject and object, internal and external. Perhaps mathematics reveals that this dichotomy is false. Mind and world aren't separate. We're part of the world. Our minds emerged from cosmic processes. Our ability to think mathematically evolved in a mathematical universe, where the universe becoming aware of its own structure. From this perspective, asking whether mathematics is discovered or invented is like asking whether a tree's Growth is discovered or invented by the tree. The tree grows following patterns in its DNA, interacting with patterns in its environment. The growth is neither purely internal nor purely external, but emerges from their interaction. Similarly, mathematics emerges from minds interacting with a structured reality. It's neither purely in our heads nor purely out there, but exists at the interface, in the relationship between knower and known. This might explain the mysterious effectiveness of mathematics. Mathematics works because we in the universe are made of the same stuff, following the same patterns, part of the same unfolding process. Our mathematics and nature's mathematics match because they're both aspects of one mathematical cosmos. It might also explain mathematical beauty. We find certain equations beautiful, not arbitrarily, but because they resonate with deep patterns in reality and in our minds, which are themselves part of reality. Beauty is a clue to truth because our aesthetic sense evolved to recognize harmony, simplicity, and pattern. As we close this season, let me offer a final thought. The question is, mathematics, discovered or invented, has occupied brilliant minds. For millennia, we haven't answered it definitively. We probably never will, but that's not a failure. The question itself is valuable. Grappling with it reveals deep truths about knowledge, reality, consciousness, and meaning. The journey matters more than the destination. What we've learned across 20 episodes is that mathematics is many things. It's a tool humans created to solve problems, from counting sheep to launching spacecraft. It's a language we invented too. Describe patterns, we discover that's a game with rules that generate surprising consequences. It's a bridge between abstract thought and concrete reality. It's a testament to human creativity and ingenuity. It's a window into the deep structure of the universe. It's a shared heritage spanning cultures and millennia. It's both the most certain and most mysterious knowledge we possess. Mathematics is humanity's conversation with the cosmos. We speak in equations, and the universe answers with experimental results. We ask questions with theorems, and reality responds with phenomena we predicted mathematically. Whether mathematics is discovered or invented, it connects us to something larger than ourselves. When you understand a mathematical truth, you're joining a chain of understanding stretching back thousands of years and forward into the future. You're participating in humanity's collective attempt to comprehend existence. Every equation you master is a key unlocking doors of perception. Every proof you follow is a path others have walked, leaving cairns for you to follow. Every mathematical insight you have connects you to everyone who has ever wondered about numbers, patterns, and truth. So as we conclude this season, I invite you to embrace the paradox. Mathematics is both created and discovered, both human and cosmic, both invented language and revealed truth. It's the overlap between mind and reality, the conversation between knower and known. The ancient Greeks wondered whether mathematics existed in some perfect realm. Medieval scholars debated whether mathematical objects had real existence. Enlightenment thinkers asked whether mathematics was synthetic or analytic knowledge. Modern philosophers dissect the ontological status of mathematical entities. All were asking the same essential question: what is mathematics? And all discovered the question is inexhaustible, endlessly fascinating, perpetually mysterious as you go forward. When you encounter mathematics, whether calculating a tip, balancing a budget, appreciating a fractal, or contemplating quantum mechanics, remember you're touching something profound. You're at the intersection of human ingenuity and cosmic pattern, invention and discovery, creation, and revelation. Mathematics is the universe thinking about itself through human minds. And you, thinking mathematically, are part of that grand, cosmic self-reflection. The question isn't whether mathematics is discovered or invented. The question is, are you ready to discover and invent your own relationship with this beautiful, mysterious, essential aspect of reality? That's the perfect place to end Season 1. But this conversation continues. The journey into mathematics never ends, because mathematics itself is infinite. Thank you for joining me on this journey through 20 episodes of mathematical history. From ancient Counton to modern mysteries, we've explored how mathematics shaped civilization, enabled science, transformed technology, and revealed profound truths about reality. And we've learned that the deepest truth about mathematics might be this: it's both created and discovered, both human and universal, both practical tool and gateway to transcendence. Until Season 2, keep questioning, keep wondering, and keep discovering the mathematics hidden in every corner of existence. The universe is speaking. Mathematics is how we learned to listen.